How you doing, all? Little ladies music for you. Daniel made it. Daniel, let's hear about this blindfolded chess plan of yours. What is this? What is this?
Well, okay, it's not so much of a plan as much as the thing I was doing. So I hopped on a Discord call with some friends. And so the friends I was playing with hadn't played chess in like 3 years. So like tried messing with time control to make it fair, but I was still kind of destroying them. So what I
Mhm.
did was okay, friend A and friend B, you start a game. I'll tell friend A what moves to make. Like I'll say e4 or knight f3 or whatever.
Mhm.
Then friend B just tells me what moves they make. Um, Longest game I've managed to win that way was like 31 moves because they hung mate in four. But it's
Oh,
a new party trick that I kind of want.
I like it. How long have you been playing chess?
Um, I learned in like kindergarten,
Hmm.
but I only started playing online like a month and a half ago.
Hmm. Are you pretty passionate about it? Like you really want to get good? It's a
No, it's just fun.
little side deal. Got it. Awesome. Thank you for telling me that. I'm actually just glad to hear you find something cool enough to stay up all night for, even though that comes at a cost. Good for you.
I mean, I was up till 3 a.m. anyways, but
Yeah, I saw your email came at three something, 3:45 or something is when I got it. That's awesome. Okay, engineering. Let's see. How are you guys doing? You got questions for me before I show you one thing from the past before we? I'm always open to homework questions because I'm teaching during class for understanding and so forth, and I'm always a little concerned that you'll hit snags in the homework. I want to make sure you can answer. You guys don't tend to ask me a lot of homework questions, so I'm not sure why, because those are not easy sometimes. Well, you can change your mind. Um, but I want to remind you of something. Let's see. All of a sudden, I'm thinking maybe I should pull this up. How easy would that be to do? Let me just double check real quick. Hmm. I think pretty easy. I think I need to do this. This is one of the things I don't want you not to learn in this class. So just give me 1 second. Dang it. That's not what I wanted to do. Okay. That was a good decision. Because it didn't take long. Okay. I just want to revisit something really quick in light of what we've learned. We looked at a project once before that involved the retaining wall being pushed over by dirt. And we're now in a position. At the time, I showed you just kind of quickly, roughly the resisting moment. In other words, the dirt wants to tip the wall over, and the house is going to push back against that, keep it from wanting to be tipped over. And at the time, we didn't understand distributed loads, and so I couldn't talk about the how much the dirt wanted to tip it over. So I'd just like to take a quick look at that again and remind you how it works. Let me see what's in this particular copy. Okay, not much. So at the time I said calculate the resisting moment, but now we're going to look at what engineers call the overturning moment, because now you can understand it. So notice down here, and I cleaned this drawing up a lot, but notice I told you here that soil, dirt, weighs 120 pounds per cubic foot. 1 cubic foot of dirt weighs 120 pounds. And we were thinking of this as a 1 foot section of the wall. And notice that's 8 feet tall, that the dirt is sitting on top of that. But, and this is something I learned from my engineering friend, I didn't know this, but geez, I think it's PSF. I think that's pounds per square foot. Yeah, it is. EFP is effective fluid pressure. So this is really interesting. I may have mentioned this to you at some place, but because dirt, does it make sense if you have water? Water isn't compressive at all. You can't compress water. And so when you push down on it, it's automatically going to push sideways. In other words, if this was water and then water weighed 120 pounds per cubic foot, then it would be pushing on the wall, the surface of the wall. And again, you got to kind of think of the wall as being 3D here, at 120 pounds per square foot. That's what would be pushing against the wall. But dirt, can you picture dirt as kind of, like rocky and stuck together? And some of that pressure is actually lost because of friction. Does it make sense? This sort of particle of dirt out here is so far away from the wall that it's not pushing on the wall very much. And so I guess this was probably done by experimentation, but engineers have determined that it's only like 1/3, apparently, 40 pounds per square foot effective fluid pressure. In other words, it's only 1/3 of what it would be as if it was water, if it was fluid. It's not fluid. So effective fluid pressure is effectively, it's acting like it was water, but it only weighed 40 pounds. That's kind of the idea. So notice this wall is 8 feet tall, but then the dirt continues on down here, and that's a foot tall. So we really have a 9-foot wall for dirt to push against. So let's just go play with that a little bit. And now let's look at how that's a continuous load. Again, I'm trying to show you practical things. So 40 pounds per square foot. This is not obvious. So you got to think about this. But that means in this first, I think I'll erase this, but in that first foot right there, that would have 40 pounds on it, pushing right there. But then the second foot would have its foot plus the foot on top of it pushing down. So it's 40 pounds per square foot. Well, that's now 2 feet under. And so this would actually go up to 80. Does that make sense? And then this one would go up to 3 times 40, which is 120, and so on and so forth. Like that's what's going to happen based on that. Because you have a stack of dirt here, and it's going to push a lot harder on the bottom as a stack of dirt than it is actually up on the top. And so, oops, what you actually have here then is a linearly distributed load where there's infinitely many forces pushing against this. And so your weight here, and by the way, Aaliyah, you sent me an email just kind of asking me about this whole integration side of this. And so I just want to, you're going to get an answer to that question a little bit here. But this is 40 pounds per square foot times X number of feet down. And that's what I just did a second ago. At 1 foot down, it was 40. At 2 foot down, it was 80. At 3 foot down, it was 120. And so I guess in this case, since I'm thinking of this as the wall being pushed on, I'm calling this distance down to wherever we happen to be X. So now that I drew that, it'll look stupid, so I'm going to fix it. So wherever you happen to be is X feet down. So this is where you're, let's say we're interested in that location right there. Well, does it make sense? If you went down 3 feet, 40 times 3 would be 120. So this arrow would be 120. If you went down 8 feet, 8 times 40, that'd be this one down here. 8 times 40, this would be 320. And if you went all the way to the bottom, 8 times 9, I'm sorry, 40 times 9, that'd be 360 down there. So actually, no, that bottom one is 360. And this would be pounds per foot. Remember, the 40 was pounds per square foot. And if you multiply it by X feet, then one of those feet would cancel and you'd get 40 pounds per foot, or in this case, 360 pounds per foot. And so again, the whole wall is 9 feet tall. So that's where I got the 9. And so we have a linearly distributed load, not an evenly distributed load where all the arrows are the same length, but a linearly distributed load. And so again, let's quickly do this 2 different ways. Again, what we're interested in is the overturning moment. Let's do this first the cool shortcut way. And that way was where you are reducing all of these forces to one force. And so what is that? What is that single force? And by the way, this is what an engineer would be doing. This is the way they're going to do it. They're going to do it the cool shortcut way. That single force would be 360. I'm going to put the units in this. Pounds per foot. Pounds, not foot per foot. Concentrate. Pounds per foot times 9 feet times a half. So what is that number? Half of 360 is 180. 180 times 9 is 1620. So this is 1,620 pounds. So all of those millions of forces added together, that's a total of 1,620 pounds pushing on that wall. And there's really weak ones pushing up here at a really large distance. Does it make sense? It wants to tip. It wants to tip over this point. So that's kind of the tipping point, or the tip point. It wants to tip over that point right there. So think moment, how badly does this want to tip over? We have 1,620 pounds, but remember what that total is a little tiny bit up here, bigger, 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 all the way down till it's at its biggest, which is 360 pounds down there, desiring to tip that over. So we got a single force, but then the second part of this is what is its location? What's the shortcut for that? What did I tell you the location was for a triangularly distributed load? We know exactly where it is. Where is it?
2/3 in.
Yeah, 2/3 in. And it makes sense. It'd be a lot closer to the bottom than the top. And so right here would be the location. 2/3 in on a triangular force. I don't know what to call that. Force diagram, force, I don't know what to call it. So that's 6 feet down, which means since it's 6 feet down, that means it'd be 3 feet from the tipping point. So now we have a force and a distance. We can now find the moment. So the moment or desire to tip is quite simply 1,620 pounds times 3 feet, which is 4,860 foot-pounds. That's how badly this wall wants to tip over. Now you don't remember this, but when I gave you this problem, we didn't know this, and so I asked you to see how badly is the building resisting this, and it was like 9,000, something like that. There's 9,000 foot-pounds of resistance, and so the fact that the wall is only pushing at 4,860 means that it's not going to tip over. And again, this is the calculations, the literal calculations and dimensions for a project that I first figured this out for. It was only about a year and a half ago now. And so that's why the engineer designed it the way they did. In the end, that footing size down there, since it's really tipping up over this point right here, that's the toe. We had all this weight over here pushing back because of the weight of the wall and the weight of the house and so forth. So his design worked, I guess is what I'm saying, because it only has 4,800 pounds of desire to tip over, but there was 9,000, nearly double that foot-pounds of moment to not let it tip over. So the engineer, if you will, didn't screw it up. That's why he got paid the big bucks. So does it make sense that if you do put dirt against a wall like that, the deeper you go, the more force there is? That's what creates these triangular loads. So that's really kind of cool. And so that 4860 is essential to calculate for a dam or for a retaining wall, because then you have to say, okay, how am I going to keep that from happening? What am I going to do to stop that? And just as a side note, the simple thing that engineers do is put a gigantic footing on the bottom of this made out of really heavy concrete. Does it make sense to get this thing to tip up now? The very fact that you have this fat piece of concrete down here that could weigh 20 tons or whatever, it's not going to be enough to tip that up in the air. So it doesn't have to be a house sitting on it. You could just put a gigantic piece of concrete sitting there to keep it from tipping over. I'll erase this, but the Golden Gate Bridge is made with this gigantic piece of concrete, and it has a cable embedded in it with probably some kind of protrusions on it, so it can't just rip through the concrete. And that cable takes off from there and goes up to the towers and kind of swings down like this. And can you appreciate that when this pulls in that direction, that this whole concrete, if you will, wants to tip up in the air that direction? Well, that's a big piece of concrete all by itself. So it's not going to tip because it's big enough. Well, you're the engineer. You're the one that's got to figure out what big enough means. If you can't get 4860 for this, then you can't decide what's big enough. Let's do this using the long cut quickly. The long cut, not the shortcut. So moment is still a force times the distance, except would you agree that our force is 40 times x? Now remember, what are the units for that? 40 times x that we had earlier was actually pounds per foot. But if you look back at I'll draw just like a chunk. By the way, if you've never seen this before, this is how people show a slice of something, a little kind of like that. There's a chunk of the wall, and so here's this force out here. And so this force right here actually has to have a little bit of thickness to it. And so that thickness, because I called the distance down x, is actually dx. So it's 40 X, which was pounds per foot, times dx, which is feet. Does it make sense then that together, 40x dx, is actually pounds? Like that's our force. Now what that is just one individual force. And so I have to let x go everywhere. I have to let x go everywhere from 0 to 9. Since this wall was 9 feet tall, I've got to let that force right there move all the way up and all the way down this. And each one of them has its own moment. So this cool shortcut that it all focuses 2/3 of the way down is a real cool time saver. But notice for that given location right there, how far is it down to the tipping point? Well, if that location is sitting right here and this overall distance out here was 9 and this distance right here was x, then does it make sense its distance down there is 9 minus x? Like that's how far down that little slice that we just looked at, it's a distance of 9 minus x feet down to where the tipping point is. So 9 minus x is the distance, and that's feet. And so wouldn't the moment then be 40x dx times 9 minus x, force times distance, except for we have to add all of those up while x works its way from every location from 0 to 9. So that's an integral. This is the long way to get the same exact thing. So if your equation, this is our equation right here that defines our load. This is a very simple, it's linearly distributed load. That's because that equation is a line. The last question on your assignment, the one that you referred to, Aaliyah, the equation was a parabola. The equation that told you how much force at each location was a parabola. So the only difference is instead of 40x, you have some more complicated equation there. So let's see if I clean that mess up a little bit before I take its integral by, let's see, multiplying 40x into 9 and x. 40x 9 is 360x. And 40 times x is 40x squared. And then I usually just kind of put the dx out here. Great, now we can take an integral. The integral of 360x is 360x squared divided by 2. You're remembering your calculus. And then x squared grows by 1 for an integral. And you divide by 3. And now I evaluate that at 9 and at 0. And I have my answer. Fortunately, evaluating it at 0 means it's 0. So all you really do is put 9 in. Guess what answer you get? 4860 pound-feet of moment. Same exact answer. That's where the 2/3 came from. I built that for you a little bit. But somebody just did this with letters instead of numbers and realized, hey, it's 2/3 of the way down. That's its location. So that's just kind of cool to see calculus and basic algebra in action. So the beauty of this is that location right there for that 1620 that we did when we did this sort of the easy way. That's kind of, well, what we started talking about when we left last week, which is kind of the center of mass. In other words, that's where the action of this force actually is. It's right there 2/3 of the way down. So the question is, let's do another example, kind of like the one we left with on Thursday last week, just because it was so long ago. So in chapter 9, that was actually chapter 4.9 again, but in chapter 9, we say, let's locate where the center of mass, centroid is code for center of mass. In other words, if I want to take this shape right here, keep in mind, this doesn't have dirt pushing against it. This shape, which let's see, it's part of a parabola. So it's like a parabola. It's been chopped off. It's 4x4, but it's a parabola. That shape is going to act according to its weight, according to gravity. So as I mentioned the other day, if it was made out of plate steel, then we need to know where the center of mass of this thing is because it's a very complicated shape. If I want to treat that like a particle, let's say that piece of metal, because of its size, 4 feet by 4 feet is pretty big. We'll say it's a 1/2 inch thick. And as a side note, I wonder if I told you that, if it was steel and you went online and you found the area of that blue shape right there, and you looked up how much does 1/2 inch thick steel weigh per square foot or per square inch or whatever. I wonder if you could figure out how much that thing weighed practically. I don't know if we have 5 minutes left and there's not time to start, maybe we'll go back and answer that question. It's kind of cool to look that kind of stuff up and see how much that thing's going to weigh. But the point is, it's going to act at its center of mass. And so if we want to simplify this shape so that we can understand how it's going to behave, we need to know where its center of mass is. As I mentioned the other day, if it's spinning through the air, it's going to be spinning around its center of mass, no matter which way it's rotating. If it's flipping all randomly through the air and it was flying through the air, rotating and flying in the shape of a parabola, if you could stare at the center of mass of it, you would see the center of mass flying in a perfect parabola. And then the shape itself would be wobbling all over the place around that center of mass. Does that make sense? And that's why it's such a powerful concept. So it's related very closely to the concept of a distributed load, just because we got to figure out where's that force located. If this thing weighs 200 pounds, where's that thing actually going to act? So the idea is something like this. If this shape was, let me erase this too, but if this shape was sitting here like this and it was like the corner of a building, does it make sense it's causing moment? Let's say it's attached to a wall or something like that. It's attached to this wall over here. Maybe it's like a plate in the corner for serving food off of or something like that. Well, it wants to rotate off the wall. Do you agree with that? It wants to like fall off the wall. So we got to kind of glue it to the wall somehow. Well, remember, it's made out of steel. It might weigh 500 pounds or something. It might really badly want to rotate off the wall. Well, does it make sense you're not going to be able to figure that out unless you can say, well, where is that 500 pounds located? If you can't know where it's located, then you're not going to be able to figure out what the distance is away from the wall so that you can figure out the moment or how badly this thing wants to rotate off the wall, and then you'll be able to stop it. That's what engineers do. So do you see why the center of mass is so important here? The load itself is coming from the weight. And moment is one of our basic calculations that we always need to get. And so center of mass is just a huge calculation. You would have spent some time with this perhaps in calculus, depending on how your calculus teacher taught it. But again, let's build it for ourselves again. So what we said the other day was really the x coordinate. Notice there's two problems here. We're going to find both the x and the y coordinate of that center of mass. And so we said this. As a general rule of thumb, we said that the center of mass around a particular location, so I guess I can put it down here, to get x anyway, to get the x coordinate of the center of mass, not the y coordinate, we've got to do them one at a time, you got to add up the sum of the moments around the y-axis divided by the area of the shape. That's what we said. So what we're figuring out is how badly does this thing want to rotate around the y-axis. Now that might, again, I want you to have a conceptual understanding of this. Why would it be around the y-axis? Well, if I take slices in the x direction, would you agree that slice has its distance? So if this is like slice 1, then that's distance 1. And notice that's a pretty tiny slice. So the weight of that little sliver that I just made is not a very big weight, and it's not a very big distance. Whereas if I go up here and I take a slice, I've got a much taller slice at distance 2, and its distance is a lot bigger. So that's causing a lot more so in order to figure out where this thing is located, kind of where the middle of it is there, that's why I've got to send it around the y-axis, because these slices have a thickness of dx. Since this is the x-axis, they have thicknesses of a little bit of x down here. But every single particle that's in that vertical slice that I have right there, they're all the same exact distance away. So that's why I've got to sum all those moments up to figure out how badly does this want to go around the y-axis. And we talked in a previous section, I'm not going to re-hit that, but why you would take the sum of the moments and divide by the sum of the distances, or in this case, the sum of the moments and divide by the sum of the areas. So to get those moments around the x-axis, isn't that area right there? Its width is dx, but isn't its height, well, the y coordinate? It's a y coordinate, you're going up, so it's height. So that area right there is y times dx. And again, that area is connected to its weight. That's why we want the area. How much does that slice weigh? And then isn't its distance x? In other words, isn't it horizontal? So we're going over a distance of x. And in a sense, what we're thinking of is kind of like that point right there is the point xy. And we're going to let that point go everywhere. That's why we're keeping them as letters instead of numbers. So that point's going to slide everywhere. So to get there, don't you go over x? And don't you go up y to get to that point if the coordinates of the point are xy? So that's its area, and then its distance would be x. And so to get the sum of the moments around the y-axis, then wouldn't I have x times y times dx? It's just kind of cool. This is just reviewing what we did on the problem that was in class. The problem we did in class on Tuesday was actually worse than this, Thursday. So let's see, I'm stuck working with x's. And so does it make sense I could replace y here with, well, notice the y coordinate is connected to the x coordinate with that equation right there. So I could replace that with 1/4 x squared. And so that's actually an integral I can take. X times 1/4 x squared is 1/4 x cubed. And that's an integral I can take, fairly straightforward. So again, I add 1 to that cubed, making it x to the 4th, and then I divide by 4. Well, there's already a 4 down there, so that becomes 1/16. And let's see, we're talking about x's, so doesn't this exist all the way from here to here? So we have x's that work their way from 4 all the way to 0. So then if I evaluate this at 4 and evaluate this at 0, I've got the total desire that that thing has to rotate around that axis, and I get 16 for that, I believe. Just doing that in my head, but it seems like 4 to the 4th is 16 times 16 divided by 16, so I think that's 16. And its area, as you know, as you knew, I should say, I shouldn't say as you know, as you used to know, its area is the same exact equation, except for you're not multiplying by x. You're not multiplying the area times the distance. It's just the area, which is y times dx. It's those rectangles. And then we just want to let that go from x is 4 to x is 0. And so again, I'm going to replace y with 1/4 x squared. Except I'm not multiplying by x. And so that integral, you raise x squared to x cubed, divide that by 3. So you have 1/4 and you have 3. I guess I'll just write it as over 12, and I evaluate that at 4 and evaluate that at 0. So 64 divided by 12 is 5 1/3, or might as well write it down exactly right, 16 thirds. So x bar then, the distance to the x coordinate of the center of mass, is 16 divided by 16 thirds, which is exactly 3. In this case, the units were feet. X bar is 3 feet. Would you agree that looks reasonable? Like there's way more metal to the right than there is the left, and so there's no way x is going to be at 2. So the fact that we're getting x to be 3, which I'm just eyeballing, is maybe about there. Doesn't that look like there's the same amount of area? I'm going to have to erase this because I'm making a mess of it. But doesn't it look like there's the same amount of area on that side as there is on this side? Doesn't that look about right? That's what center of mass means. Same area on the left as on the right. I guess I don't need to erase that. Please interrupt if you're finding yourself thinking, I'm just not seeing this. Because before we're done today, we're going to go 3-dimensional with this. These are 2-dimensional shapes, but what about 3-dimensional shapes? So you've got to conceptually understand this, or that's going to feel really weird. So since I destroyed my picture, would you agree that the centroid, the y component of the centroid, is going to be the same exact concept, except for I'm going to have to put my slices this way. So that's still the point xy. There's my y-axis. There's my x-axis. This is still the point xy. And notice the thickness of my slice here is a little bit of y, but you got to think a little harder here this time. How long is this distance right there? It's not x. X is the distance to right here. You understand that? And because we were told this thing existed from 0 to 4, does it make sense the distance all the way to here is 4? And so that little distance then is apparently 4 minus x. That's the size of that little slice right there. And like last time, that distance up is y, because the y coordinate of this point right here, the distance up is y. So if I want the sum of the moments, same as last time. Notice this time though, it's the sum of the moments around the x-axis. Then that would be the area, which we figured out was 4 minus x times dy. There's the area of our rectangles. But those are a distance y away from the x-axis. So there's our integral. Notice this time we're stuck with working with y values though, because I have a y and a dy. And we are lucky in this problem with respect to symmetry that the y coordinate, the highest y coordinate, is also 4. I don't think this is a good problem for that reason, because it makes it look like the limits of integration are always 4 to 0. But they're not always 4 to 0. They just happen to both be the same here. And then because I'm stuck working with y, does it make sense I have this equation y equals 1/4 x squared? The problem is I really need that x right there. I need that x in terms of y. Well, can I solve this by multiplying both sides by 4? And if I square root both sides, the square root of 4 is 2 and the square root of y is the square root of y. Does it make sense? That's my ability to replace x with y. So let's see, what do I have then? The integral of 4 minus 2 square root y times y dy, and that's working from 4 to 0. Now, just as a little side note, engineers do not take integrals. Integrals can sometimes be very hard. You probably were good at this, if you're lucky, last year, or like Aaliyah emailed me, I think it was like 6 years ago that she took calculus. This is probably feeling really foreign to you. But let me just show you what, I'll show you this from the top. Engineers don't take integrals. They let machines do them for them. So your graphing calculator will do this, but I'm just going to show you this on Desmos. No, actually, I'm not. Yes, I am. Desmos. We're going to do it on Desmos. So our equation, I'm going to call it, no, I'm just going to write it out. So over here on the right under functions, under miscellaneous, there's an integral sign. So Desmos will do integrals for you, which is kind of cool. So we said from 0 to 4, we wanted to know 4, let me see, was this what we had? 4 minus 2 square root of y? 2 square root of y. I'm tempted to make this an x, but I'm just curious to see if it'll work even if I use a different letter. So I got to get out from under the square root. So I'm hitting an arrow. I'm closing the square root off. And there was a times y. And then there was a dy. Interestingly, notice it's not giving me the answer yet. It won't give you the answer unless you actually go in there and put dy in. Boom, there's the answer, 6.4. So notice I did not have to take an integral. I had to know how to set the integral up. Interestingly, when you take calculus, the books tend to do this exactly the reverse. In other words, they give you a whole bunch of integrals like this, and then they ask you to take them. But what happens in the real world, you don't have to take the integral. You just cheat to take the integral, but you got to write the integral yourself. No one's ever going to walk up to you in engineering and say, hey, can you help me solve this integral? You have to write it yourself. So that's kind of cool that, you know, this is actually applying things that you learned in a calculus class. So this is not a particularly hard integral to take. If you multiply y in there, you get 4y minus 2y to the 3/2 power. It's just a power rule problem. But just because it's kind of cool, I think I'll stick that into the notes for you to steal. Crop. So apparently that is equal to 6.4. And so if I want y bar, I have to take 6.4 divided by the area, which I already calculated. Was it 3? I forgot. No, 16/3. That was the answer. The area was 16/3. So again, I'm just typing that in my calculator. What is 6.4 divided by 16/3? I got the wrong answer. It's 1.2. It's equal. Didn't even have to round it off. 1.2 is y bar. And again, that's feet in this problem. So if I look at this drawing up here, does it make sense to you that it would be up 1 foot up in the air? Not very high. So if this is 4 feet, that'd be 2 feet. There's 3 feet. There's 1 foot. So about where I drew it is about right. It's a hair above that. Doesn't that look centered? Like these two coordinates, X bar, Y bar, we got to be 3 and 1.2. That's kind of the huge takeaway from this. So now I know how that thing's going to behave. As a side note from my picture, notice, and I probably will have to erase this because it's going to make a mess, but if this was attached to the wall right here, like I described, so we're looking down on it like it's a table, does it make sense the fact that you know how far it is away from the wall now allows you to kind of figure out how badly that table wants to rotate and break off the wall? So, you know, how strongly do you need to screw it or glue it to the wall, if you will? You now have the ability to attempt and answer that question so that you can do your job and keep it static. So talk to me, Evald. How are you with this? What percent are you there? 99. I'm almost there, but I'm not perfect. No, like 40. Give me a percent. I want a percent from everybody. Evald, how are you?
Okay, not 100%, that's for sure. Just need a little bit more practice. I mean, we have this as a homework, right?
Yep, you do.
Yeah.
So you're feeling.
So, what is that?
You're feeling decent. So you're saying like what percent then? 90. You said not 100, but you implied that you were kind of.
Yeah, maybe like 85, 90. Yeah, something like that.
Okay, fair enough. What about you, Daniel?
I'd say 85, 90.
85. What about you, Leah? You should be worse. I don't know if Aaliyah's can totally connect, but she said it's been 6 years in her email since she had calculus, so she's probably worse. How about you, Ben?
Yeah, about the same as everyone else.
Okay.
I think I was trying to take the integral, by hand, and for some reason I'm not getting the right answer.
Well, let's do that really quick. It never hurts to be good at calculus. So if you distributed the y in there, then you'd have the integral from 4 to 0. 4 times y would be 4 times y. Do you agree that the square root of y is y to the 1/2? And so you have y to the 1/2 times y to the 1, which is actually y to the 3/2 because you add those exponents. Do you agree with that?
Yeah. Also, Aaliyah said something in the chat, I think. So
In the chat, awesome. She's there. Thank you for telling me that. Proportionate x bar. Yeah, so I don't know if you read Aaliyah's question, but she said she's curious why it wasn't proportionate. In other words, why wasn't it 3 foot and 1 foot? Well, that's because it's not a circle. It's drawn to look like a circle, and if it had been a circle, it would have been symmetrical. But because it's a parabola, it's not symmetrical. So it's steepening more quickly, if you will. Like the circle kind of looks like this, and a parabola is going to go like that, kind of get steeper a little fast, which drew the y bar up a little higher than 1. That's an awesome question. Yeah, and so she said, yeah, I'm still kind of getting my calculus skills back. So that's about what I would have thought, Aaliyah. So did you get here, Ben?
yeah, I did.
So then the integral of y to the first would be y squared divided by 2. That'd be 2y squared, because I'm going to add 1 to this and then divide by 2. 4 divided by 2 is 2. When I add 1 to 3/2, unfortunately, I got to do common denominator. So 3/2 plus 1 would be 3/2 plus 2/2. That'd be 5/2. So minus 2y to the 5/2. But then I have to divide by 5/2, which is actually multiplying by 2/5. So I have 2y squared minus 4/5. Y to the 5/2. And I'm going to stick in 4 and stick in 0. Fortunately, 4 is easy to stick in. 4 squared is 16 times 2 is 32. And then y square rooted. 4 square rooted is 2, and 2 to the 5th is actually 32. So I can do this without a calculator. That's 32 times 4/5.
Okay. Now I'm getting the right answer. I must have plugged it in my calculator wrong first
Yeah.
time.
Easy to do. And so that should produce 1.2, which it does. 1/5 of 32. So kind of cool. Now, all shapes, though, are not this nice. So let's drag another shape in here. This problem is actually easier, but it just may not look like that from the start. So this is kind of a cool looking I-beam. So let's just stare at it for a second and think about what that I-beam is doing. This is actually somewhat realistic. So let's think about this. First of all, can you picture what this actually looks like? Like this would be the shape. I'm going to erase this because it's going to get in the way, but think about this shape as a beam. Let's say you had it supported over here and it was supported over here as well. Does it make sense that's going to want to bend down? I've been talking to you guys about this, and it's going to be really important in the very next section. But if a beam bends down, do you agree that there's going to be cracks that form in the bottom of it because the bottom is going to be under tension? The bottom is going to want to tear apart. Well, can you see the brilliance of not just having that beam be made out of wood, but having a giant piece of steel down there? Does it make sense? The bottom is actually under tension, and I've mentioned this, getting longer. The bottom's going to get longer, but this midline right here actually doesn't change at all. It doesn't change shape at all, which means the fact that this beam has kind of nothing in the middle of it, just a tiny little skinny web, that's brilliant. You don't need that much stuff there. What's happening to the top? Well, the top is actually crushing together under compression, and so you got this giant, much thicker piece of steel up there in the top. And so this is the principle behind which I-beams are designed. Usually I-beams look like this, where they just have rectangles on the top and the bottom. But the point is, you want lots of stuff at the top, you want lots of stuff at the bottom, whatever form that might take. But this is kind of a cool design. Maybe that bottom is a cable or something like that. Well, awesome. There's a little bit of a primer on this cut. Why this is kind of a cool shape. But notice they're asking us to find its location Y bar. And then down below, wait, there is no X bar. How come they're not asking where the center of mass is left to right on this shape? Who can tell me the answer to that?
Because the shape is symmetrical, so you can assume that's in the middle.
Exactly. It's symmetrical. This is not a weird, unusual shape like we just tackled a second ago. This is like a circle and two rectangles. And so we already know that it's somewhere on that line right there. Does that make sense? We know it's symmetrical left to right. So we don't care what X bar is. We don't care where it is left to right. That's a duh. All we need to know is where is it vertically. And notice they drew it in for us just as an example. Would you agree with where they drew that? Do you think it's a little higher than that, a little lower than that? Remember, it's reasonable because what they're saying there is that this area to right there is identical to this area down here. Do you think those two areas look identical? I don't think where they put that's too bad. Do you? That's what we got to figure out. Where is that? So that those two areas are identical. That's it. Now in this shape, there's no equations, but that's because those areas don't require equations. Like I don't need calculus to find the area of a circle. I know the area of a circle. The area of a circle is pi times radius squared. And you guys know that it was calculus that gave us that formula, right? But it's an algebra formula. And you know the area of a rectangle is base times height. So it's like I don't need to do an integral problem to find the area. So let's do exactly what we just did, but without calculus. And we'll kind of call that our x axis. Notice that's where the measurements are being taken from. Do you see how they're saying y bar is the distance down from that axis up there? So we're going to find the sum of the moments around that axis. Well, we need two things. We need the sum of the moments and we need the area. But in this case, and this is in 9.2, not 9.1, I forgot what the title of that part of the book is, but it's, actually maybe I can look in my notes and see. Yeah, it's called composite. This is a composite shape. It's two rectangles and a circle. And real shapes are composites, like that I-beam I drew a second ago. That was 3 different rectangles. But would you notice that in this I-beam, and I'm designing these in houses all the time, would you agree that shape is not only symmetrical left to right, it's also symmetrically vertical. So you don't even have to do any math. The center of mass is right there. But that's a composite shape, three rectangles put together. But our shape is a little weirder than that. It's got circles in it. And so again, we need two things in order to find the answer that we're after, which is y bar. We need the sum, and I'm going to write the summation symbol this time, the sum of the moments. And again, we'll say about the x-axis here. And I also need the area. And in this case, I'll say the sum of the area because there's 3 of them. I got to add them all up myself. Integrals are where infinity is involved, but in this case, it's a Riemann sum if you remember your calculus, because there's just 3 of them. Like I can actually add them. I don't need to do calculus. I'll just add them up. So let's go get those. What is the area? Let's see. So 1, what's the area? Well, isn't the area, let's see, pi r squared. I'm told down here that the radius of that is 50 millimeters, excuse me. So pi times 50 millimeters squared. And part of me is thinking, do I need to convert that? I'm looking at the dimensions now. They're all millimeters, so I guess just leave them alone. So there's that, plus there's that 15 by 150 on top. So 15 millimeter times 150 millimeters sitting on top. So I'm getting millimeters squared for my areas. And then the one in the middle, hey, that's exactly the same size. It's also 15 by 150. So I'm going to say times 2 instead of writing that whole thing again. And so what do I get for the sum of all those areas? I get approximately 154.44 square millimeters. That's how much area I have. Didn't need calculus. Notice they said, which I think is kind of cool, or did they say this? Neglect, yeah, they did. Neglect the size of the corner welds. Do you notice they drew those in there? Like those have to be welded together, and isn't that weight too? And so that was nice of them to let us off the hook with that, wasn't it? Because that would have been kind of hard to calculate. Seems like that would be tiny, and so I could neglect it. I can see why they did that, but it's kind of cool that they drew them in, but also said, you know, don't worry about it. Then we need, secondly, the moments.
doing the area on my calculator. I'm not getting the same thing.
Oh, I think I wrote the wrong thing down. I did.
Oh, okay.
I think I just wrote down the final answer. I was looking at a sheet. Thank you for saying that. It's 12,353. Is that what you got, Ben?
Yeah, that's what I got.
So I didn't want to waste time putting that all in the calculator. It's kind of a duh that it's not 150, right? Look at the numbers. 150 times 15 all by itself is already way over 150. So that was kind of dumb not to notice that. So that circular area, earlier was 7853.98. How far is that away? Like, remember, it's the area, which again is kind of synonymous with its weight, because ultimately area is going to turn into weight since this weighs something. How far is that away? What is its distance? Where do I measure to? Where does that circle act? Where does its 500 pounds of weight act?
At its center of mass.
Yeah, at its center. So notice its center of mass, because it's a symmetrical shape, is locatable based on logic. So that's its distance. So for the circle, just like last time, I'm taking a area times a distance. It's no different. So I'm taking 7853.98 square millimeters. Let's actually leave the units in this and think about this for a minute. Times a distance of, well, notice I got to do a little bit of math here. I've got 15 right there and 150 right there. And then the radius of this is 50 as well. So I've got 215 millimeters. Isn't that its distance? You agree with that? So times 215. Wow, I get a gigantic. And the reason I wrote the units in is, what are the units of this? Notice the units are not like foot pounds. They're, well, this is millimeters squared times millimeters. This is actually millimeters cubed. Isn't that weird? But as a side note, because you might look at that and think, wait, how can that be a moment? It's not a moment. If it's millimeters cubed, where's the weight come in? Well, remember, if you multiply this by the density, if let's say this was metal and it weighed 10 pounds per square millimeter, because it was flat steel, if you multiplied its density times this, notice the units would be pound millimeters. It would actually be, in other words, that's weight comes in when you add a density to it. So just as a side note, that's not as weird as it looks. So similarly, the other shapes, let's see. One of the rectangles. One of the rectangles, well, 150 times 15, we didn't write that down, but that was 2250. So same thing. So I have 2250. I'm not going to write the units in this time, times its distance. Well, this one right here, since that's 150, then halfway up would be 75, and 75 and 15 is 90. You agree with that? So I get 202,500 cubic millimeters for that rectangle. And then the top rectangle is exactly the same size, 2250, but its center of mass is right there, which makes it only half of 15 away from the x-axis. So it's times 7.5. which is only 16,875. So if I add all of those up, I get 101,907,981.051 cubic millimeters. So now we have everything we need. What do we do to find y bar? What did we do in the calculus example? We take the sum of the moments divided by the sum of the areas. 0.98, roughly, should have just called it 12,354. And you get the answer I accidentally wrote down earlier, 154.44. Notice the units. This is cubic millimeters. This is square millimeters. When you divide those, you get millimeters. Of course you do, because y bar is a distance. So even though we didn't, and what's fascinating about this is you don't have to know what the thing weighs. If this stuff was light as paper, it doesn't make any difference. It's still going to be the center of mass. Do you see how we kind of didn't even need to get the density involved, because the units came out of distance anyway. So it doesn't matter what the density is as long as they're all the same density. If there were 3 different types of steel there, then we would have had to got the density involved, the weight of each one involved, because they weigh different amounts. So they're saying then, or we're saying then, that y bar, which is that distance down right there, is 154 millimeters. So to get to here, we said it'd be 165. So backed up a little bit right in there. Yeah, that does look about right, doesn't it? So we didn't need calculus to get this one right, but it's just a composite of shapes, and many things in the real world are like that. If you look around the room, do you notice the same thing? Very few things are just one thing. I'm looking at the lamp sitting next to my desk here, and it's like it's got a shade on top and a base on the bottom, and so, you know, if you have to, then you could break it into individual pieces. It doesn't matter how many there are. There could be 20 of them, not just 3 like we had, and it's going to take more time. That's kind of cool. Not hard. But now, let's just do one more example. I'm sure we'll run out of time with this one, but some things in life are, you know, flat. Everything we just did there was sort of flat steel or flat wood, but there's also 3-dimensional things. And so the important thing here is to note, hey, this is a 3-dimensional shape. Would you also agree, and you should kind of recognize this from calculus, notice the axes they're giving us are kind of weird here. This is the z-axis and this is the y-axis. And they don't even show us what the x-axis is. But this is kind of like, well, a parabola, because one is squared and one's not, even though the letters or the axes are weird. One is squared, one's not. That's a parabola. It's a parabola that's been spun around the y-axis, and so this looks like a bullet, perhaps. I don't know if you can think of other things that looks like. That's the first thing that came to my mind, but it's like this solid piece of metal. Well, of course, I need to be able to find the center of mass for that, for the same exact reason. I need to know how this thing's going to act. So before I had a flat table in the corner and that was flat. And so I can only think of that as a 2D object. But if it's 3D, then it might have an X, Y, and a Z bar. But in this case, notice because it's spun around the Y-axis, again, it's symmetrical. So I know the center of mass is somewhere along that Y-axis right there. What I don't know is how far in is it. Notice for that reason, they're asking us for Y bar. That's the only thing that we need to know. They didn't ask us for Z bar or X bar or anything else. That's it. Y bar, because I know it's along the Y-axis. Given that this shape, if I draw it from the side, kind of more bullet-like like this, given that they're telling us that that's 4 meters deep, where would you say the center of mass is? Is it right in the middle at 2? Is it a little left of that? Is it a little right of that? Do you have a sense? Is that a duh to you?
It'll be close to the thick end.
Yeah. There's more weight on the right of this. It's not going to be there. It's going to be more like over here. But this time, would you agree what we're looking for is not the area to be the same on both sides, but the volume. I need the volume that's on this side. I don't know if I can even draw this. I need that volume over there to match, well, this volume over here now. So it's like volumes I'm comparing in order to find that. And so in 3D, it's the same exact concept. It's just that in 3D, I'm going to have to find the sum of the moments, in this case, around the Z-axis. But I'm going to be dividing by the, and I think I'll use calculus here instead of, but it's going to be divided by the volume, not an area. Does that make sense? And as a side note, to get the moment, I'm going to be taking a volume times the distance, not an area times the distance like we did last time. So it's no different, except instead of area times distance divided by area, now it's volume times distance divided by volume. No different. Make a nice, decent sized picture of this from the side view, though. So oddly, they told me this is the Z and the Y axis. So my shape is right here. So as before, this is such a cool concept in calculus if you understand it. Does it make sense to get to that point? I had to go dink, 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 dink over a distance of Y and then up, dink, 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 up a distance of Z. So that's kind of like the point YZ. If you took Calc 4 with me or with somebody, then maybe that XYZ axis isn't quite as mysterious as it used to be. And so let's go get the volume first, the sum of the volumes. Let's go find out what the volume of this shape is first. And again, we got to use calculus to get this. But the key is really, the key is, as it was before, I've got to make a slice of this thing. But because it's 3D, would you agree that the slice isn't, well, quite as simple as I just drew it? It actually looks more like this. It's kind of a, depending on how calculus went for you. The slice is cylindrical. And by the way, just as a side note, in engineering, you know, in modern days, like you're going to draw something in a 3D drawing program, and it will tell you the volume of that automatically. Like I have AutoCAD from 2004, and it'll tell you that if I draw this shape and just say, what's the volume of it? It'll tell me. It'll even tell me the center of mass. Maybe I'll have a chance to show that to you. But it's kind of cool to do this sort of the long way. And so if I want the volume of this, don't I have to take that slice and I have to slide that slice everywhere from the left and to the right. I got to slide it until it sort of bangs into things. And notice I'm told that it's going to bang into y is 4 and it's 0. And so it's between 4 and 0. So I've just got to add up all those cylinders. Well, would you agree that the cylindrical slice has a volume of pi times radius squared times h? I mean, you got to look that up. That's the formula for the volume of a cylinder. Again, we are indebted to calculus for giving us that formula. But do you agree that in our case, that z right there is our radius? Isn't that the radius of our slice? And isn't our height right here, isn't that height a little bit, a tiny amount of y? Since it's horizontal, just like the y-axis is horizontal, it's a tiny amount of y. So therefore, the volume of my slice is pi times radius, which is z squared, times height, which is a little bit of y. And so I just need to add all those up. Again, I've got z's and y's, but because of dy, I'd really like to work with y values. And notice they were very nice to us, because what's the connection between the two worlds of z and y? Z squared is equal to 4y. Oh, that's really cool. That means I can replace z squared with 4y, and then everything is y. So I can say, then good, y is from 4 to 0, z squared is 4 times y. Awesome, everything is y's, and so that's an integral that I can take. Again, just as a reminder, I might have more success since the constants just come along for the ride if I just pull those out and ignore them for later. And so the integral of y to the 1 is 1/2 y squared, as you know. And now I can evaluate that at 4 and 0. And I don't want to forget that there was a 4 pi sitting out in front of that mess. So 4 squared is 16, divided by 2 is 8. So I get 8 times 4 pi, I get 32 pi. Were there any units associated with this? Yeah, meters. So this is actually cubic meters for volume. I don't know if you stop to think about it, but it's like, yeah, that's a pretty gigantic shape. 4 meters, huge, 12 feet. So I found its volumes. All right, well then what about its moments? It's time to change colors. What about the moments? Well, it's no different. It's just that I have to take that slice right there, the volume of that slice, which is its weight, and multiply it by how far, since we're going around the z-axis, I have to multiply it by how far away is it, which is y. So I'm taking its volume, which is kind of like its weight. Last time we took its area times its distance. This time we're just taking the volume of the slice. That entire slice is all exactly the same distance away. That's why I sliced it vertically. So the only difference is you're taking its volume, pi times z squared dy, that's its volume, times its distance, which is y. Last time it was an area times the distance. This time it's a volume times the distance. Again, I got a bunch of y's there, and so I want to replace the z squared with 4y. So I have 4y and a pi. So again, I'll pull the 4 pi outside. But I end up with a y and a y. So I have y squared sitting in here this time. And it still works its way from y's of 4 to 0. So if I take the integral of y squared, you add 1 to the y squared, makes it y cubed, you divide by 3. And again, I'm going to evaluate that at 4 and evaluate that at 0. So 4 cubed is 64. So I end up with 4 pi times 64 thirds. When I put 0 in, I get nothing. So I don't even have to sort of subtract. So 4 times 64, I think, is 128. No, it is not. It's 256. Good thing I checked. So I get 256 pi over 3. And notice I took a volume, which was cubic meters times the distance in meters. So this is actually meters to the 4th power, which is kind of weird to think about. So just like before, I've got everything I need. I've got my volume and I've got my moment, and I can now go get y bar, which would be the sum of the moments divided by the sum of the areas. And meters to the 4th divided by meters to the 3rd is going to be meters. The answer to this will be in meters. I can see that the pi's cancel. I'm in the mood to be lazy. So if I take 256 divided by 3 and then say divided by 32, I get some decimal. I use my calculator to convert it, and I get 8 thirds for this. 8 thirds, or approximately 2.67 meters. The question is, does that make sense? So Daniel answered the question back when I said, where would it be? Given that this thing is 4 meters long, since it's thicker on the right, wouldn't it be past halfway? So it's like 2 2/3 of the way in. Yeah, that actually kind of makes sense. Something somewhere past 2, but way before 4, like 3. 3 wouldn't have surprised me. 2 2/3 doesn't surprise me. So that actually kind of makes sense. That's kind of cool that that works. Yeah. So here-ish. Yeah, makes sense. I think that's true. That's pretty cool. So from a practical perspective, I'll erase this, but now that I know that, if this thing weighed 5,000 pounds and you decided you were going to glue it to the wall using some kind of construction adhesive, there's 2 things you're worried about. One of them is, will it just slide down the wall? Can the glue resist the desire to go down vertically? Can the glue push back? Can it create the friction to push back against that so that it won't slide down? The second thing is, will it actually tip away from the wall? Well, that's a moment calculation. You now know where that's located. It's located a distance of 1 1/3 away from the wall. So if I take 1 1/3 times 5,000 pounds, does it make sense that would be the moment or the desire that thing has to tip off the wall? And then you could say, okay, is it, glued on, bolted on, good enough? Do you see why this is such an important calculation? Why center of mass is so huge? Really powerful stuff. All right, I'm seeing 12:24, which means time to shut myself up. So my advice to you, if you have time, would be to go, because I don't really need to show you anything else about 9.1 and 9.2 to be successful. I might do another problem that's 3D next time just to kick it off, but we're probably going to jump into chapter 7 because it's such a stinking cool section and so powerful, so important, called shear moment diagrams. And so if we had an extra hour on that, that would really be awesome. So the best thing you could do is get 9.1 and 9.2 due before Thursday, so that if there was a problem, you could ask me about it. But I will leave that to you. All right. Stay after and ask questions or get out of here.
did have a question. Is our latest, when is our project on My Open Math due? The one about the trusses, was that already due or?
I kind of forgot about that question. I would say it's due nowish, like get it to me right away.
Okay.
Let me see real quick. I think I just posted it in there because you guys are going to email it to me. Yeah, you should get that to me soonish.
Okay.
And by the way, like, don't just turn it in randomly. You're more than welcome to ask me, hey, this is what I got. Is it right? And if it's not, fix it, because there's a lot of button pushing involved, and it'd be easy to get something wrong, even if you understand what you're doing. So you should get full points on it. And if you have to go fix it, then go fix it.
Okay. Sounds good. All right. Bye, Doug.
Yeah.
Yeah.